whole house is
Okay, so just so you know, we changed a bit the schedule. We're going to start with the orbital feeding. So we have more time to see that. That's maybe more important than. I'm not. No, everything is important, but, but the reason is that so the person doing the Starship presentation was supposed to record it so we could play it at any time. But we couldn't do that. Had a problem, technical issues. So I want to see if he can present calling in, but he's in California, so it's too early. So we'll do it later. And if he cannot call in, I guess you can give it. We have the presentation, so Neil can do it. So yeah, we're going to start with that.
I guess before like I began talking about Orbitize, has everyone been able to like install it? I think that's a big thing. I know.
How many people have it installed right now, or how many people do not have it installed right now?
So maybe take like 10 minutes. I don't know.
Yeah,
or first to like make sure that everyone.
Okay, so I'm
I want to make sure everyone has Orbitize working.
Is it just pip install?
How many people do have it up and running?
You have to do something else first to upgrade it and make sure it's up to date, and then it's pip install Orbitize. But it's like pip upgrade Python, and it wants to make sure. I'll pull it up actually. Orbitize.
He's uploading your presentation?
Yes. So I'm gonna post the page in the Slack. So here you can go in this website that I just posted on the Slack. I usually do this first. Well, I did this for every machine I did first, and it definitely did something. And then I did pip install Orbitize. But if that doesn't work and you're on a Windows machine and it's like breaking, there's a workaround where you can just get it from GitHub, git clone it. And then you may have to delete the README because in Windows it freaks out. And then you can do Python setup.py install, and then it should work. But let me know if it doesn't work.
For now, I think we can do only like a import advertise. We don't know whether
only for PTs.
Yeah, we don't know that. I mean, it imports properly, but we don't know until you send your.
Oh right, yeah.
If it's actually
Well, that's a
running.
start. That's a good start.
Yeah. No, but I think if it imports, I think it should be fine. The problem usually is not even like it fails at the install. It gives some error, right? Is that what you were struggling with?
So on Windows, it fails with pip install because of PTMC.
Yeah. So I think the workaround might be to git clone it and delete the README file.
Yeah, me too. That's kind of what kept me from starting with. Gotten better. So, what do you use? I usually use pip. Pip is bad. Pip is bad. I know you're. I will tell your conda 100 times, 1,000 times. Same thing. I use pip.
I'm also gonna send 2 papers on the package. Are very useful because
it's all working.
Yay! Okay. But yeah, the papers are really good because she's really good at like writing it at a level that any person can understand. So I want to share it with you. Yes. No, I didn't. It's okay. I'll do it later. It's only like 3 slides.
Okay, so I put the notebooks on the.
Okay. Yeah, no, the slides are not important, but if anyone's interested, I'll share them later, but for now, it's okay. It's only like.
It's a bunch of.
Question on the, oh wow, so I'm here, right?
Yeah, it's a 13 minutes.
So maybe, so it's feeling like PTMC. So this was if I do install PTMC.
Okay.
So the reiterate me.
If we don't use some of them, I remove some to not confuse people.
Okay. I wonder if it would help. If I can find. It's in the README file. I don't know. So I guess it's all
You're a proper New Yorker. Although Times Square parts, they would be found dead in a.
because even so I can't pick these ones.
Not realistic without being immersed.
Huh? That only fit your
Yeah. Well, I think it's so crowded. I think it's like very touristy. I've been there a few times, but I'm over it. It's too great. Even staying out in Elba, the night where the sky never. It's just so bright. Anyway. It would never not allow the crowds. How's it working?
Yeah, it works.
Sorry?
Yeah,
it
it
works.
should, yeah.
I checked.
Okay.
You have to, you're stuck there for maybe an hour. No, even when they go to the bathroom. Oh, Georgia.
Oh,
From India. Well, it's all about context. Yeah.
No, I have my own. I didn't know, I never used it like before.
They're not being.
Having enough people. It's a good business where I live. There's nobody. I wonder, I mean, you could, I guess, I have a fear of crowds. When I get to see people like that, they have
Where do you
agriculture,
get
which
it
is
from?
It was installed on my computer.
feeling like not
Yeah, I
safe.
think it was installed first.
Okay.
In the middle of nowhere, if it's too crowded.
Like for example, when I came,
The architecture might say.
I have it on my phone.
here in safe, but
Yeah,
I was in Michigan, so like an urban city.
Oh, yeah, Detroit's kind of scary.
Not so many people walking.
Yeah,
People
oh.
walking.
Oh, I see what you're saying. A few times.
And you get the
Everyone else have it like installed and maybe running. So the first notebook, I should specify where everyone starts doing
Yes.
things. The first one will be formatting input. Because that one will produce files that we will need for the rest of them.
It is in the box.
Yay! Oh! I'm so happy. Okay, great. Awesome. Everyone else got it working then? We're all good?
Hold on.
Yay. Oh,
It's like one of these eureka moments that only happen once in a lifetime.
I hope this is not.
It's the best moment in research when I managed to run this notebook.
That would be very sad.
okay. So I think we all got Orbitize working, or at least like being able to import it.
It's a sum of lot
Which is
of little
good.
moments like that.
So what is
It's the
the
little
Python
things.
notebook we need to look? What is the notebook we need to look?
Formatting input is the first one, but I'm gonna talk a little bit about the background on it first, and then we'll do that.
Oh, okay, cool.
Alright. Okay, so Orbitize, oh, I like failed here. So Orbitize, the name is with an exclamation point. Sarah would be very upset at me. But the package, Orbitize, is actually a great package for orbit fitting, I've found. So it has two, what do you call that? Like two ways that you can orbit fit, and you can use OFTI, which is orbits for the impatient. And then there's, and then you can use MCMC as well through here. And so what Orbitize does, either for OFTI or for MCMC, is that it takes input table with RA and DEC offsets that are actually obtained through VIP or PyClip or any of those packages. So once you have those RA and DEC offsets, you can actually use that table and input it into Orbitize. And then you can actually get orbital elements from it for the given planet that you have detected. So the great thing about Orbitize is that not only does it take RA and DEC offsets, but if you have separation and position angles, that it also takes that as well. And then the RV measurements, it is almost like close to being, I've been talking to the group, the Orbitize group, and they're really close to pushing it to a new, like, to Orbitize, like pushing a new update with RV measurements, which is great. Hopefully it'll be done either before or during the data challenge, so that if people want to implement RV measurements with their astrometric measurements, they can do so, which is really great. And so, yes, this is just the list of the 8 orbital elements that it returns. And so basically OFTI, the way that it works is that it generates an initial set of parameters of the 8 parameters. And then what it does is that, so here's the generated, the initial orbit. And so what it does is that it scales and then it rotates it. And so after it does that, it goes through a rejection method where it compares the likelihood of that orbit with a random number between 0 and 1. And so that way it, that way it rejects or accepts orbits. And so the more orbits, the better. And so that way, that's why OFTI is different from MCMC. So actually, OFTI is optimized for coverage of small fraction of the orbit. So the smaller the fraction of the orbit, the faster it runs actually. And I'll show that why later in the notebook. And so this is just an example of what it would look like, you know, when you run it through Orbitize. And so this was for the last hack day, or I think this was the previous one maybe. Yeah, I only have 2 planets, yeah.
Those the answers?
Yeah. Not the answer to the new data challenge, but,
Okay.
but no, but yes.
Can you go full screen just to see?
Oh, yeah.
Better on
Is there,
you
I've
just
never
view.
Very bottom, it says enter full screen.
Yeah, I've never done like full screen on
The only thing is that
PDFs.
you cannot go back to normal.
But yeah, anyway, so this is just like an example of what the output will look like. You get the measurements for however orbits you give it. So if you want 1,000 orbits, you tell it, I want 1,000 orbits, and it'll give you 1,000 accepted orbits. And so then you can plot the distribution, and then you can like try to find the median and be able to find the values for the orbital elements.
Doesn't the number of orbits you ask for impact the error?
Sorry?
Won't the number of orbits you ask for impact your error, or no? I guess it makes it fuller.
Yeah, so the bigger the number of orbits, the better, because
Yeah.
it'll constrain, yeah, so
Okay.
it'll definitely like, yes, it will affect your errors.
Okay.
The less the orbits, the larger the error.
Okay, gotcha. But the longer it takes.
But it should eventually converge.
Yeah, it
right?
should eventually
Same
converge.
distribution.
Exactly, yeah, so.
Okay, that's what I
yeah.
thought.
So anyways, that was a very short introduction, but I think it'll be better now to go to the notebook. So, so then,
Can you zoom?
yes, how do I?
So you do like command
Apple
plus, Apple plus
Even my,
command.
Cloverleaf.
Command.
one.
Oh,
I'm used to the old.
We call that an apple.
No,
okay, got it.
Yeah.
Apple two sheets.
I'm learning
You can
something
actually see
every
all the
day with that. Okay, so yeah, so this is one of the trickiest parts not the trickiest parts, but like trying to make sure that the input is the correct way so that you can run Orbitize smoothly. So it's just like a very short notebook on the steps that I took on the data that we have. So you should have 4 CSV files for 4 different planets. And so those files are from the last hackathon. And so they have flux ratio, the error on the flux ratio, they have the epochs, they have the time span, and then they have the RA and DEC offsets. But for input and Orbitize, you can't just input that into it because it needs to be, formatted. And so you will have to like get rid of a bunch of rows and add a couple of columns to make sure that it's in the readable format. So I don't think, I didn't save it, but in the website, I don't know why, here it is, actually. The link is here. And so you can actually go and see for yourself the format that they want for their table. So it can either be in this format with these headers or with these headers. So we'll explain. The link is in the Jupyter notebook. But anyways, so if we run it and we take the E planet, which is the farthest one out, then we see that here in these tables, we actually have NAN for those that are not detectable at those epochs that you wouldn't be able to see in the HLC in this case. So I should say the first 4 epochs are HLC and the last 2 epochs are star shade data. So for example, this planet would only be visible in star shade, not in HLC. And so we don't want to work with this because we would only need these 2 to input into Orbitize. So then here you have to index the rows that you would like to remove. And so you just print the table a bunch of times to make sure that you can see that it's actually doing the right thing. And then we remove the columns that we can't input into Orbitize. And so we see that we like get a more reduced version of it, which has all the information we need. But we need to rename the columns because they're very specific about how they want you to name them. And so we rename them here. And so one of the things that Orbitize makes you specify is whether it's an astrometric measurement or if it's an RV measurement. So the way you do this is you just make an object column and you use 1 for an astrometric measurement or 0 for an RV measurement. So we don't have RV measurement here, so we just use one for all of them. And we add that to the table. And then we convert the epochs. The epochs have to be in modified Julian date. But it's in Julian date.
How does it matter why there is a difference, astrometric and RV data? It's like its position, right, always?
Well, it just needs to know.
Yeah, so Orbitize needs to know, if the RV measurement,
It's physics.
yeah, it's like, how do I explain this? So it needs to know whether it's an astrometric because RV will take into account the star and the RV measurement is just taking into account the position of the planet. So it does some physics to it. But yes, that's why. And so, yeah, it has to be an MJD and hopefully you all can use this very simple notebook. Obviously, it will be modified because all these steps were taken for this specific table that we had for the hackathon. But whatever you get from PyClip or VIP, it's gonna look completely different. So you're gonna have to modify it. And pro tip: don't use pandas for this. Doesn't work.
Don't use
Interesting.
pandas?
Like, yeah, if you want to modify your table, do not use pandas. It does not take it. I discovered that.
What are pandas?
Because pandas, no matter how much you try,
What is pandas?
What's pandas?
pandas is a package.
Okay.
Yeah,
It's
so,
to handle like
Yeah.
tables.
yeah, but the problem with pandas is that I found out, no matter how much you try, it always has to have an index. And so for Orbitize, you can't have an index, like it won't take it. And so there's no easy way other than you can handle the table, but then you would have to go manually and take away the 0, 1, 2, 3, like the index at the beginning. But this is the easiest way that I found just with AstroPy, easy, simple.
Question?
Yeah.
And then I noticed for the table that had nothing in the value, in the CSV table, I always get that in the drugstore confused. It had not a number, NaNs, in that cell. So what happens if it's a blank cell? Do you need to put the NaN? How does it handle a blank cell in general? Do you need to go ahead and make sure any blank cells have the NaNs in them?
I guess that's more of I actually don't know can tables have empty cells, right?
I don't think they can sometimes.
they?
You have to
I'm not
actually.
They might have a special, like a none.
Yeah,
Yeah,
there's
so
none
maybe
too.
like that.
So go ahead and maybe make all your empty cells
Yeah.
NaNs. if
So
they're
yeah,
not.
maybe for convenience, so you can see.
Yeah.
Yeah, maybe that would be good, and that way you can pinpoint which ones you need to. But also another thing that I would like to say. So here, our job was made easier. Neil made our lives easier here because he put NaNs on there.
Yeah, he did.
But in if you get a measurement, but it's like the flux ratio is not detectable, then it wouldn't be a measurement that realistically we could make and input into Orbitize.
Do you need all of those variables in order for Orbitize to work? What if you don't?
Yeah, so you need at least one of these three. You need at least either RA and deck offsets, either separation position angles, or RV measurements. Either one of the three.
But not flux ratio.
No, it doesn't take in flux
That's
ratio.
Okay.
So that's why here in the notebook, I take it away. I actually remove
Oh,
here.
I'm sorry. Yeah.
No, it's okay.
Okay. I see.
Yeah, so I removed those columns that we don't need. Well, we need them, but Orbitize doesn't input them. But yes, but it is useful to have because with this we know that it's detectable in the first place. And so yes, so that's what we do. And so here, I don't know where I left off. Yeah, here, we're able to get the final table. And then we have to write it again as a CSV file because Orbitize only takes either CSV or, actually, let me see, what does it take? It's an ASCII file. I read it somewhere that it takes either LaTeX or
Takes LaTeX?
I think so, yeah.
Okay.
It's something like that. It's in the paper. I can't remember. It's in the paper about Orbitize. It says the specific formats that are accepted, but don't do pandas. Like it will freak out. It won't work. And so the easiest way I found was just using AstroPy table, and it worked.
Oh, it's in it.
And so if you all want to take a couple of minutes to run this for all four, so for all 4 planets, so here you can just change this letter here. It can be from B, it goes from B to E. So if you want to change this to B, and then here, remember to change the name so it doesn't overwrite it. And then once you do that, display the data, and then modify according to the table what rows you need to remove. Which, by the way, it has to be individually like this. It doesn't take like the colon for some reason. It doesn't work. So you have to individually put the rows like this. And then after that, everything is pretty much the same for all of these tables. So you can do cell, run all below. And that way you don't have to run it so many times for for the other 3 planets. Does that make sense? Is that good? Yeah. So yeah, you will need these files for the other notebooks, by the way.
Oh, we need to do this?
Yes,
on the other
yeah,
file?
sorry.
Oh, have you shown
Said
the
it
format?
might be different.
Do you run it all the way and
Yes.
save the
Sorry,
file?
I'm on the wrong tab. Okay.
Okay. Yeah, so at the end, you should be, yeah, in the end, if you run it all the way through, you should save this file. I think that's the error you're getting. It's like, oh, can't find the.
I got it. Okay.
We need to change the path name as well.
I think the B or E or whatever it is after the IP.
Planet. I see, okay.
So that
This is good. Oh.
Is it command?
yeah.
It's going, yeah.
Yeah.
Oh,
This makes me very happy. Thank you so much. Congratulations. No. It's never gonna happen.
no, I will be very happy if you can do it without.
If I'm ever self-sufficient again, I would be so happy this never can happen. I always code things that I want to learn.
So then, planets.
Okay, so then we need to go here.
Yeah,
So
that's
here
fine.
change
You're getting
Spacing,
hilarious.
And here the name too. And then, well, if you run those 2, then,
Okay.
yeah. If that, run that, then run that, then you have to adjust which one you delete.
I did you.
Oh,
So which
By the way,
is, so I had, it starts from 0 to 1.
Okay.
the same.
Yeah.
Yeah, that's what I was.
Not really sure what it says. And then after that, you can honestly do, yeah. You can run one of the big stuff.
So
0.
Yeah.
So you would have to run it again. 'Cause-
Okay,
Yeah.
right, yeah.
So you have to run again the initial data. Yeah.
No, no, no.
Because it already deleted it,
With
so it
route.
delete the other
Delete.
ones.
Oh, yeah.
Yeah,
Okay.
it's,
I think you have to tell it which one to.
and you can do honestly kernel,
Oh, yeah.
not kernel, cell,
He does,
run all below. Well, I think you did all above.
This one?
No, I didn't.
yeah.
She didn't ask.
It's the motion they.
Okay.
No.
And then now you have the refined, and you can do the
When I
same
was
thing.
working there, he had to transition.
So the only part that really needs your attention
He
is
was-
making sure that you use the right.
He was trying to have.
And then after that, you can just run it,
Yeah.
run all below. It saves automatically.
Right. We need to do this right
Yeah.
after all
Yeah.
these minutes. Okay. Just out of curiosity, is there a way to
He's a
get,
great
how
guy.
would you get this to just print out like what these, instead of just float sheets or, oh, it does, it is. Okay.
Yeah, you are right.
Great.
No, there's not, we never start.
How much time?
How's everyone doing
Hours,
on
like-
the? You good?
Yeah,
I saw your hand.
I renamed my output. So for the case of B, like, so it's like this. B, so we need to play with
Yes. So when you change the planet's name, you need to make sure that when you output the table, the first step, you have to change the rows that are deleting. So it needs your attention up until the rows, and then after that, it's pretty, just go straight down, you can do run all below.
Don't you want to change the name of the CS?
It's already there, so at the beginning, when you change the planet name,
Yeah.
the file in the bottom
Oh, I
already
did
uses
do
that
it.
name.
Oh, yeah, look at that, I have 2 letters.
Yeah, so it already takes it to the
Or if he
planet
wants
name.
to see what else here.
So after I run below, and then it'll change it.
Yeah.
So I planned it like
Staying here for the rest of the day, right? There's no.
Yeah.
They're like, oh, check this out.
That's a good point. Yeah.
No, I swear it worked.
Yeah.
So if you go up, so you would change it.
It had to be the old.
We're doing
Um,
that.
here two, and then here two.
I know.
And then after that, you print out the data.
You could.
That was awesome.
Oh my God.
And then after that, you can do cell,
That
run
is
all below.
Cool
So
and
you don't need to like
disappointing at the
rewrite
same
this
time.
again, like
Like,
last cell, because you can just run this.
yeah.
Them all in.
Which lab was that for?
Maybe it was like. Although I did make decisions that.
That was July.
I just
Not my style.
I have, there's like 10 of us. It'll come. Okay, we get.
Is everyone okay, at least with B or like at least another planet that you can use in addition to E? Yes, thumbs up, yeah. Yay, okay, great. Okay, so now we're gonna head over to the OFTI tutorial. Oh, I need to. So I just want to say the other one, most of these tutorials are online. I just modified them for our data challenge and basically for our needs. But most of the work I have to recognize that it was Sarah and her team. So most of these notebooks were made by them, and I want to give credit. Yeah, they can be found online if you want to try it for something else. But this is, these I modified for us for the WFIRST Data Challenge. So, so AFTI, here's the link to the paper. I already sent it to the Slack, but if you want to access it really quick, here it is. So this is just teaching how to use AFTI. And so, we choose the star, that is 47 Yuma. And we know from Neil's notebook that we can get it from Sinbad. We can get the parallax. So we get the parallax from there. And so for AFTI to run, it needs the CSV file for the planet. And you need to specify whether you're using AFTI or MCMC. And then you have to say how many bodies are in the system. Right now, AFTI and Orbitize only takes in one planet at a time. So this is, right now, we always say that it's one, because otherwise I think either breaks, or if it doesn't break, it just runs forever or something happens. But Jason Wong is working on it. He's doing great work on this, and hopefully will also work. But for now, we can treat each planet as, as the only planet in the system when you run it at a time. And so you give it the total system mass. We just give it, in this case, the star's mass, which we say it's around 1 solar mass, because 47 Yuma is very sun-like. Because we also don't know the mass of the planet. That's part of the data challenge, to be able to come up with mass measurements. And so we input the parallax. If we have the parallax, all of these are optional, but if we have them, we can input them, and it'll help with our output. So since we have the parallax, we put in the parallax and the error. And so, did I run this? Okay. Yes. And so what driver does is that it saves everything about the planet into this driver and about the system. And so from there, you can then use AFTI and specify how many orbits you want accepted. So I think it says it in the bottom of the notebook, but most, for a good convergence, and like if you're gonna publish a paper, it says like you should run around like 100,000 to 1 million orbits if you want it to but it runs quick. But like if you wanted to converge and wanted to publish, you should do that. But for now, since we're going quickly through this and it's a tutorial, it was actually 1,000, but I upped it to 10,000 because it doesn't take that long. So if you run it, you'll see that it takes a couple of seconds, doesn't take too long. And so basically, yeah.
Sorry, does it work with multi-core? Okay, does it take the advantage of
For
if your computer has more cores, does it combine them to make it faster?
That's a good question. I don't know. But I imagine that it would.
Maybe ask Jason Wang.
I don't know, but I would think that if you have more cores, it would be better. But anyways, so here in run sampler, all this does is that it does the same process of scaling and rotating 10,000 times. It goes through that process every single time until it accepts the number of orbits that you want. So I didn't change this, but it's 10,000 because that's the amount of orbits that we gave it. And so here, if you print orbits, 0. That gives you all of the 8 parameters that I said at the beginning, the semi-major axis, the inclination, what else, eccentricity. It gives all of those for every orbit. So whatever index you give it is a different orbit. So here is the legend, basically. Yeah, so semi-major axis, eccentricity, inclination, argument of periastron. I forget what it's. Then the parallax and the m total. Yeah, let me go back to refresh people on the real quick. Oh, not that. I believe it. Yeah, so okay, argument of periastron, position angle of nodes. Oh, pan. Epoch of periastron passage, and parallax and total mass. So those are the 8 parameters that we get. So then after that, we can plot them. Yay! Pre-plots. It's my favorite part. This just has some explanation of what the process is for it, but you can do then. You can then plot the distribution of the 10,000 orbits. So you can see that if you zoom in, goes around here. That's a very bad limit. Maybe I should change that, but
So we have 2 points in the orbit. I think we are.
Did you just switch to a different
orbit
notebook?
out of them.
Opti tutorial.
I just uncommented the PLT.
Okay.
Here, I just uncommented
Oh,
that,
okay,
yeah.
got it. Okay.
So, but then here, yeah, so here you can see this semi-major axis,
That's what I'm asking.
and then down here you can plot more of the parameters. It's really cool because you can see them, and how well, even with just 10,000, this is not even like 100,000 or to 1 million orbits for publication, and it's still already, giving a good distribution. So
It's an interesting distribution that I get for that.
So for the orbital semi-major axes, if I, yeah, yeah. So if you see here,
I don't know what this is. Oh, he's been to. Oh,
Yeah.
for Planet E.
you see that it's somewhere between 9 and like 16.
Have you tried? Sorry, go ahead.
No, go ahead.
Have you tried running this with B? It took like 10 minutes and only from orbit.
Yes. So you're ahead. Do you try it with B?
Yeah, and also if
Yes.
you plot it, I guess maybe it doesn't look very good.
Yeah. Okay. I was actually gonna talk about that later. That's why I'm using E,
Okay.
because there's a reason why it doesn't run at first.
I'm sorry, how does that
Sorry,
Opti, so it generates the 8 initial parameters, just 8 random initial parameters, and then it scales and rotates to fit with the planet.
Okay.
Yeah, and then it does that, and then it goes to a rejection method where it takes those values and then it compares it to chi-square likelihood with a random number. I can't remember very well what exactly compares it to.
Okay, but it's in
0
the,
to
it's in the
1.
paper that you.
Yes, it's in either Orbitize or the Opti paper. It's definitely there.
Okay, I'll take a look at that. then.
Yeah.
Thank you. Sorry.
No, that's okay.
I had a question. So from the 2 data points that we had, it generated 1,000 orbits and also predicted 8 properties of the orbits.
Yeah.
Okay.
So
From 2 data points.
every orbit has 8 parameters.
Right.
Yeah, and so what I did is that all of those 10,000 orbits were expected in terms of its likelihood. So it was more likely that orbit actually was
Where is the
closer to
likelihood?
the truth value.
Where is the likelihood?
So it's not there, but it's just it's in the bottom of it. So I'll get to that.
Okay.
Yeah.
But how come like two points just make a line, or
Then we make it orbit.
Yes, I will get there. And then, so then after that, you can save the results to, well, you can access the results through s.results. So if you remember s, where is it? So s is a sampler, is where you store all of those values that you got when you ran OFD. And so you can access the results from that same class. So here you can get a corner plot.
Yeah.
You can see it doesn't converge very well. You would have to run it more, but it's still pretty good. But yeah, here, this is where they said minimum of 10,000 for convergence, and for pre-plots, 1 million.
So if you, the only thing you have to change here is just the driver name, right? And here my driver equals.
Yes.
And then just, so when you run it, got it. And so running it for V, as I think Michael just pointed out, no, you don't get anything.
Yes, and I will explain why.
Okay.
Yeah. So here are the pre-plots.
So with MC, yeah.
So you can get, so this is start MJ Epics.
No, I didn't use it.
Don't run it, it may break for you. I know it broke for me. I think it's a bug in the code, so I'm gonna have to contact them about that. But you can at least plot the orbits. So here, I believe it's plotting, I think the default is 100 orbits of the 10,000 orbits. You can choose however many orbits you wanna plot. You can choose how many epochs you wanna plot. And so this just shows the different parameters. So here the position angle and the position angle of the separation, and then the orbits, which is pretty cool. So yeah.
So what does it mean to say
Can't trust that.
epochs like a scale like that? Are they just the number? It's not like the number of
So that's
years.
for the epochs is like like what we have in our table, like the epochs for each observation.
Okay, so
So
they're
it's
meant to
interesting.
show dates.
Yes, so
Oh, so it's like 100 years of.
yeah. So the idea with start MJD is that it doesn't plot that many, and you can choose where you want it to start, but it's failing. So I think there's a bug, and I need to tell them.
Okay.
Yeah, it doesn't work. Maybe someone can try it and let me know if it works, but it didn't work for me at all, and I tried a bunch of things, but yeah, it'll like constrain like where it starts and what it shows. And then there's like a couple of other parameters. So yeah, so the default is 100. The start MJD is this one. You can choose the epochs to plot, and you can change the size of, if you want it to be a square or you just want it to be a random, like either a rectangle. You can choose whether you want it to show a color bar or not. And yes, so a bunch of other things that are in another notebook, but we'll get to that. Anyways, I'm gonna run through this really quick, but this is just to show like the more in-depth explanation of, so driver is a very easy way to get it working and get it running quickly. But if you wanna go through it very carefully through every step of the, right before it runs the 10,000 orbits, you wanna make sure that every step you're handling. So here you have this part and you have this sampler, and then here you have the prepare samples. So you have the 10,000 and it's the initial parameters for the 10,000 orbits. And so yeah, so these are randomly generated orbits that have been scaled and rotated already, but are the initial ones. And so then you can see here the different shapes. And this is, and then, so once I'm just gonna read what it says there because it explains it very well. So once our initial sets of orbits is generated, the orbits are vetted for likelihood, which is what I was mentioning to you, because it's a rejection sampling method. And so it computes the probability of an orbit based on the chi-squared. and then it compares it, where does it say that? That rejects orbits with the lower likelihoods, yeah.
I'm really lost right now. Where are you in the file? I
Oh,
think this is explained too fast for me.
sorry.
There's OFD and API. I don't see where. Oh,
yeah.
you're way down there.
Yeah.
So now when I'm running, I don't get any plots at all, and it doesn't matter which planet I put in. I don't know why.
You try E.
Yeah, which was making plots for me before.
Oh,
not doing
because it's
anything.
still running, so maybe stop the kernel. If you stop
Oh,
there.
I see. Okay.
So here,
Stop.
here.
Stop.
Yeah.
Okay.
And then and then if you go down, you can run the E.
Okay.
You can run this again, yeah.
Thank you.
Yeah, there's a reason why I'm only using E right now. So if you try B, it's gonna not work.
It's pretty tricky too.
Yeah. So anyways, this just goes through all of the steps that go into being able to generate, get the accepted orbits. And so this is just like a more in-depth steps of running OFTI, but you don't have to do that. Driver is simple. But if you want to make sure that everything is how you want it in terms of the numbers of orbits that you want, then you would use this more advanced way of doing it. And then you can save your files using these, the H5PY files. And so they save it this way, but I actually have found this is the best way for me to access my results if I'm loading it up again. So here they're just saving the orbits and that's it. So they're saving all 10,000 orbits with all of their 8 parameters, which would be great. But if you want to use later, you want to use the likelihoods, you want to use their chi-squareds for other things, then this is the best way to do it, because with results you can access the likelihood, you can access a chi-squared, you can access all of those things that if you do with orbits, you won't be able to see it because it's only saving the orbits. But that's more of a preference thing. What you want to do with your data.
Is an HDF5, is that like a Python save file?
I don't even know what it is, but it's a file that you can.
I know what it is, yes.
Yeah.
So HDF5 isn't just with Python. There are other things that you can. It's sort of a more convenient way of saving library structures. So there are readers for it that are much more intuitive.
And so, okay, I think people went ahead. So you've probably seen that if you run this, you try to run this, it just doesn't do anything.
I have 2 now.
I have 4.
So definitely stop it. You don't want to break your computer. It doesn't break it, but it will take literally an hour or half an hour or something crazy. And so does anyone know why that happens? Does anyone have any ideas why it works so well with E but not with B?
Is the orbit not physical? No.
Not necessarily, because we saw that we have astrometric offsets, and we
Yeah, but it's not a.
yeah.
It's making a triangle and not a.
That's true.
That's what I meant by physical.
Yeah, that's true. That's a good point. Yeah, but you can trust that these are very physical. Yeah. Does anyone have any ideas?
It's having a hard time finding ones to not reject because it has to fit through 5 lines, and just picking a random point, rotating it doesn't often give you a fit.
Yeah.
Can you say that again? Can you rephrase?
So it's having a hard time finding orbits to not reject because the chances of picking a random point and stretching and rotating for it to go through 2 points is very high. But when it's 5 points, it's very low chance that you'll go through all 5 of them perfectly. So it's going to reject almost all of them.
Oh.
So this works worse with more data?
Yes. Well, more specifically, it's not specifically that if it has more data, it's bad. It's what I said at the beginning, it's a fraction of the orbit. So OFTI is optimized for a small fraction of the orbit. But if you give it, so planet B, it seems that it's 5 epochs. It covers either a large fraction of the orbit or the entire orbit. So it will not work. Because OFTI is optimized for that, which is good because direct imaging, usually, you can only see like, in epochs, you only get a very small fraction of the orbit, generally, in direct imaging. So if you, but it's okay because you can still use MCMC to then get planet B and the other planets that may have problems with it.
Can we do something about that in the reject option? Like,
that's true. You can also go back to the rejection. But I think that the samples, the rejection part takes in the number of samples. So you would have to just reduce the number of samples, and it would still take a long time.
Actually, I have a question.
Yeah.
This should be at most half the speed of MCMC in the worst case, because if your rotation give you a rejection, you can just still sample the unrotated one and have the MCMC speed. So all you wasted is the matrix computation to choose the rotation. So I don't know. I just think that should be part of the code so that it doesn't get stuck in this case.
Yeah.
So that you still have the baseline MCMC speed.
Yeah, that's a good point. So yeah, I definitely was very confused at first when I was learning this. Like, why is it not running? But yeah, I think in the paper they either address that or they talk about that. Comparing the speeds and comparing their comparing MCMC to OFTI and their time and their convergence. So. But yes, okay, yeah, definitely stop that. You don't want to run that for forever. You can do here. You can just click this. You can stop stop it. Okay, so now we're gonna head over to the MCMC. Any questions? Sorry, any questions about this? About OFTI?
You guys have it so easy nowadays.
This is really nice. Sarah and her team have done an amazing job. This is a really nice package. Okay, so let's head over to the MCMC tutorial. I don't even know if to talk about this, but so yeah, you'll see they have explained very well. All of this has been them. This is their tutorial I just adapted to us, but it's very well documented.
Zoom a lot.
Oh, right.
So you don't see anything online.
Yeah, it's the online camera is really low resolution.
It's not for people online because we're recording. So
Yeah. No, that's a good point. Thank you.
See.
Yes. So now we'll use MCMC. We use the parallel temper version of the affine invariant sample from the PTMC package. And you can use either one. You can play with that. And so we can read in the data the same way that we have done for the last 2 notebooks. Should be pretty straightforward. You can choose MC parameter, you can choose the walkers, you can choose the temperatures. It says up here what you need in order to reliable for convergence.
Did we do a really cursory overview of what MCMC is and what it's doing at any point during this that I perhaps didn't pay attention to yesterday? Would that be worth a quick, because I don't know what walkers are, this is not
you know, this is now for a slightly foreign language, maybe if we just do a quick
Yeah,
cursory description of what MCMC is,
yeah.
that'd be helpful.
Does someone want to
Yeah, I was gonna say.
volunteer?
Yogi.
I can give you the 15-second version.
Let's do a couple 15 seconds versions. Like, I'd like to hear kind of the description from a couple different people, if that's okay.
Yeah, no, that's great. That's a great
Yeah,
idea.
right on the
Even for
wall.
me, I'm like.
Yeah, you can write on the wall. We have.
Yeah, there's that one.
We have
Whiteboards.
markers. All these walls are whiteboards. Also, there is a whiteboard right there. That might be. Yeah.
What's easiest for people to see? Do you want to also come up? We can.
Well, I want to hear yours first, because.
Pressure.
That's great. Okay.
Good idea.
I am by no means an expert on MCMC, so if I say something dumb, please correct me. Because I don't want to mislead everyone in the room.
Can you stand here so we can?
Yeah. Actually, I think there's like a
She
mention.
needs
The
to be by
middle.
the
Because that's like what
whiteboard.
I'm gonna. I was
Ah, you're gonna
Yeah.
use that, okay, because.
Needs the
we don't
whiteboard.
have- Yeah, it's true.
Yeah, but
Or we
But
can
you
use,
can also use that paper.
we can use
and
this
pen.
one,
can we lift this up and?
Oh, there you go. Yeah, let's do
Yeah.
that, but we need to shut the projector down, otherwise it's just gonna be on there, so.
Well, this is gonna be recorded.
Oh,
This
yeah, I
means
don't
that
know.
more than the people in this room get to see me.
We
beat
can
down.
cut it out if you don't like it.
No, it's okay. I
We
mean,
can
you
cut
would-
it out, yeah.
Okay.
You can actually write on the wall, yeah.
Yeah.
We need to stop the
It's
project.
gonna practice for all your.
Should I just turn, like, shut it off?
Well, but
No, 'cause I
the
think it'll
majority
show
of my
the
work is
camera
not on
You do the blunt,
MCMC.
thing, you know.
Oh, oh, that's a good point.
There you go. Okay.
Sorry.
Oh my god.
One way to do it.
I feel like
Something's gonna
Just
burst
see
into
smooth.
flame.
Pay attention.
Okay. So, the basic idea of an MCMC is that you're trying to optimize some sort of model to fit your data. So, you have a model that you're testing that has some parameters. And then you have your you have your data. And effectively, sort of at the core of it is you're going to be doing some sort of optimization to determine, you're trying to minimize basically the difference between your data and your model. And so the way that you do this is we could imagine that we will start with one walker. So you have one little walker that is going to be going, let's say you have 3 parameters. So you have your walker that starts at some initial position, and it calculates the value it calculates the value of your model, compares it to the data. And then what it does is it says, okay, well, let me vary each of these parameters. So I go from here to here. Or they don't all have to look the same. And it calculates again, and it compares. And so it does this iteratively. And so when you have when we say walkers, you have more than just one thing that's exploring your parameter space. You have a bunch of little, we can think of them as little guys that are walking in your parameter space and testing your entire parameter space to say, okay, what does my model look like here? What does it look like here in the parameter space? And it's comparing it. That's sort of the fundamental thing that an MCMC is trying to do. So when we say a walker, you want to have at least twice the number of walkers as you do parameters. I'm not entirely sure why that's the case, but I know that that's the case. But if you have more walkers, you're sampling your parameter space more quickly. You also sort of have to run it for a certain number of steps. So the reason you run it for a certain number of steps is that you want all of your walkers to begin to converge on the solution. The more steps you run it for, the longer time you're giving it to converge on a solution.
Sorry, what's the difference between a step and a walker?
Right, so a
I always
walker,
get confused in that.
yeah, the walker is the little guy that is doing the stepping around the parameter space. The step is saying, okay, I've done an iteration where I'm exploring a new region of the parameter space, or I'm checking a new combination of parameters.
Does that, so the
One
step
walker
is the
going through
thing,
many steps.
yes, the
Oh,
step
okay.
is the thing the walker is doing.
Okay, okay.
A walker is kind of like the number of samples. You're sampling at the parameter space.
Yeah, it's the number that you're sampling at the same time. So like, one thing you could do, I'm sort of just thinking that the latest data run that I've done, I had 50 walkers and I had them going for 2,000 steps. I could have done 10 walkers for 10,000 steps. And I think that you can get similar results, but I think that when you have more walkers, you're able to sort of see the convergence on your parameter space more effectively.
And of course, the number of walkers you choose will impact the speed.
Yes.
So obviously you want an infinite number of walkers.
Well, but so does the number of steps, right?
Yes, right.
So, so sort of both of the things affect the amount of time it takes. Yeah.
But I think
But relevant to like what, and somebody asked about multiprocessing earlier, you can basically have several processors running independent walkers, and so
Yeah,
you
right.
can get like, you could run everything for longer and do 1 billion steps.
Yeah.
Or you could run, 4 or 8 chains at the same time. And then
Absolutely. So that's the benefit of.
Well, it's more subtle than that because when you have, it's not perfectly parallel because it's a markup and you care about where the other walkers have gone.
Yes.
so there's like sample space rejection
Yeah.
methods to like.
Yeah, so it's not quite as simple as like, oh, if you have 8 threads, you can use 8 walkers and it's fine because, as Michael's pointed out, absolutely the walkers are dependent on each other.
So I think you briefly mentioned it, but I was wondering about the correlation between the number of walkers and the parameters in the model.
Yeah, so I think that you need to have at least twice the number of walkers as you do parameters. And so again, so this is getting to the this is my basic understanding of what an MCMC does. The specific intricacies and like the special things are by no means something I'm an expert in, and if people have that expertise, I would love for them to provide it. But like this is sort of this is my like basic understanding that I'm like, yeah, I know it well enough to use it now, right?
And you should be careful to make sure you're kind of using different starting parameters and stuff and kind of spreading out your walkers because it could kind of get stuck in probability valleys, so to speak.
Can we talk about the probability functions, like the distribution set?
Yeah, so the benefit of an MCMC rather than like just a simple optimization is that an MCMC is theoretically supposed to help you avoid getting into those local minima. It is trying to spread walkers out into a wider parameter space. The thing you have to be careful for is sort of the constraints you set on your walkers. So if you set that too narrow, then obviously you're going to run into your boundary. But if you took some set of initial conditions and then just did like a classic optimization where you're just going to like the lowest value, then you can definitely pick up in some local minimum. As an MCMC, it's supposed to try to sample.
What are the temperatures? Like, I know I've seen that a lot. Do you know?
Temperatures.
Yeah, there's a part in the thing. I remember reading about it.
I'm not sure.
Okay.
I've
also seen that.
Sometimes you use Boltzmann sampling so that you make a Hammett. So instead of sampling the probability, you pretend it like some kind of energy, and then you calculate. You sample according to e to the minus e over p. So it's as if you're minimizing the Hamiltonian instead of maximizing the likelihood.
Yeah, well, MCMC here uses like temperature, so that's why.
It's like it's a different physics, I think. I just Googled it. It's a different area. They use annealing method, like or not annealing, like
Simulated annulling.
annealing. Yeah, so it's like a.
That's supposed to be fast on quantum computers. I don't think it's any faster than on quantum.
Yeah.
No, we need to worry about that yet.
So no, there's a quantum, there's a quantum annealer built in Vancouver that has 4,000 bits. Does every annealing in one step. So,
Oh my god, I forgot that was there.
Yeah, yeah. Like that.
How warm is it?
That's not warm. It's cool, like-
It's hilarious, probably like hot.
White markers?
Was that sufficient for people for an explanation? I mean, because I was.
Oh.
Oh, great.
That's a diagram that I like.
Yeah, let's look at it. Let's have a look.
Oh, yeah.
Thinking of random walks.
This is from, by the way, a coursework slide, so please don't.
Nice.
That's a very simple, like one walker or one, you're just jumping, like, and until you get a high probability.
Interesting.
I have a really stupid question. At each point, at each step, what is it evaluating the probability of exactly?
Oh, so
Good question.
That's a good, yeah.
if you have these data and you know that you have some error, right? And then you have a curve that's like this. So you think, okay, I can actually calculate the probability that if the real model is this and the uncertainty is this, what is the actual probability of seeing this particular realization of the data?
I see.
So that's gonna be some product e to the,
Like
x
some
minus mu
squares
over
of.
this. Some, it's
I mean, does it basically come down to just the residuals and the?
Squares.
Okay.
Chi-square.
Okay.
Oh, that is chi-square.
Yeah. Yeah. Okay. Thank you.
Feel good. That was great. Thank you so much.
Thank you.
Great. All of you. Yeah. Thank you.
Like,
Okay, so now that we have some understanding of MCMC, then we can run through this notebook. So yeah, the reason why I was asking about the temperatures is because here, I feel like I've read it in either in here or in the paper. I'm really sorry, I can't remember. They explain really well the temperatures in MCMC. Increasing the number of temperatures further ensures your walkers will explore all of parameter space and will not get stuck in local minima.
Okay, so the temperature might increase the steps that it will jump around.
Yeah,
Kind of like
way good.
like molecules bouncing around.
Yeah. Okay, good. I knew that I had seen it somewhere. I'm like, it's there. Yeah, okay, that makes sense with everything. Okay, so actually, yeah, with the local minima, the temperatures would then help with that. Okay, great. So yeah, with MCMC here, we read it the same way still because it's still the same package. We specify the number of temperatures, the number of walkers, the threads, and then yeah, we save everything in the driver, just as we did with OFT. And then we run it. This is again, I don't even know if it converges because this is for our own data and it's not even taking into account other things, but it runs pretty fast. And again, like if you want convergence, maybe probably run it for more.
What are all these runtime warning things?
I don't know. They also had it in their. I've been having these errors. I have to ask them about it because yeah, I wanted to check if I was the only one getting these, but if everyone else is getting these, yeah. I mean, it still runs and we still get results and we can still visualize them, but I don't know what they mean and I don't know if they're like important, to take care of. So I would have to.
Trying to take the log of negative.
Oh, what are you?
Goes in MC also, and I guess it's sort of.
Trying to look at what the variance of
What's happening there?
Camera should almost be pointing at this right here. That's a much better resolution.
yeah, but we wanted to have
You had Python 3? Maybe something.
So
I wonder if this is something to do with how I install.
if it's
Right, and also you can look at that and say like, like, it's not really relaxing into our real parameter.
Why does Orbitize
So like,
use
when we
MC
look
rather
at
than
this,
MC?
I have
Why does
potentially
it use PTMC rather than
one
MC?
very bad one. Because it just, yeah, I know.
I was using MC.
Yeah, because I use MC.
Yeah, I'm not sure. I feel like they may have addressed it in the paper.
Sounds like they're really
Can't
confused. She said, she's like, or we could just give you the.
But
whole
anyways.
thing. That sounded like something that she didn't recommend.
So now the run is complete. The walkers have done their job. Good walkers. And then we can just look at the yeah, we can look at 5 randomly selected walkers for 2 parameters in this case. And then we can see how they change here. I don't know why they're not. So I'm pretty sure this is semi-major axes. This is a step. Probably have different things. So it's just a way to visualize if you want to look at your walkers for specific parameters or just a couple. And then we can also just chop the chains. I think, maybe correct me if I'm wrong, but chopping the chain maybe is helpful because at the beginning, it's taking some time, right? It takes some time to start converging to the true value. So we want to chop it off at the end, at the beginning. And then I guess at the end, they do it here at the end too, maybe, not sure, but maybe at the beginning. So that you can do that here too with Orbitize. You can just chop them up. And then you can, again, you can get the corner plot, of course. And then you can see the parameters as well. And so actually we can also visualize it the same way that we did with OFT. Might not look as great, especially if no one changed it and we're running planet E. Then OFT's orbit, OFT is optimized for planets like planet E. So that's why OFT was created in the first place, because with MCMC we see here that does not look as pretty. Yeah.
So because we're basically not seeing it find like some consistent group of stable orbits, is there a way to, like, I guess, in our, what distributions are we supposed to be finding in like the corner plots? Like what's the real orbit for this?
Like the orbit.
Like just comparing, like if we wanted to look at what the orbit for the planet actually was and compare it to just like the weird spread of orbits that we get out of MCMC here, how much better does OFT actually do? Is the next notebook a comparison between the two?
There's a notebook that compares them, yes. Yeah. But anyways, yeah, no, that's a good question. But all I know is that OFT, because of the rejection method, it converges faster than MCMC, and like even MCMC, even when it takes a long time, it may not even converge as well as
right, because like there's no other. I guess I'm struggling to figure out like how, like of course MCMC would do better with more data, but I guess I'm not quite sure why OFT does better with less data. Like the rejections, it's because it's looking for orbits to reject rather than randomly finding orbits to not reject. Because basically MCMC isn't rejecting, right? And OFT is looking for things to like
Yeah.
No, it's still
So,
it's still Metropolis Hastings.
It is.
It's just finding so the reason why I work with less data is because like say you have only 2 data points and you can always from any. So look, when you're scaling and rotating, that means that out of all the orbital parameters, you can change semi-major axes and you can change the omega, but you cannot change eccentricity.
Yeah.
So that means that given a fixed eccentricity, can you always draw an ellipse between 2 points? Yes, you can. So that means that you're automatically finding a legitimate solution. Whereas for Monte Carlo, your A can be way too small or way too big. So it's finding the best possible A.
You
and
have a
omega.
more constrained problem.
No, I just think it's that given the other 4 or 5 parameters, you're already finding analytically or pseudo-analytically the best A and best omega, so that it just uses a symmetrical problem to guide you towards the minimum first and then sample.
Okay.
But when you have more data, you can't solve for the intersection.
Yeah, another thing with OFT is that your error bars are very small. It's gonna take a long time too. Yes, so as we can see, for Planet E, it hasn't converged as well as OFT, which is why OFT was created. It's much faster. And so we can save the results as well in the same way for MCMC. And so yes, so that's how we run both OFT and MCMC. And so another thing is that I think for both OFT and MCMC here in Orbitize, you can modify your priors. So if we go to the modifying priors notebook, this is directly from the website. This I didn't like change at all. So you can see here it has like some sample data they give. But you can still run it. But anyways, this just shows very quickly that you can modify the priors very easily. So one thing I think what Sarah Blunt was talking about the last hackathon is that she wanted to use the posteriors from Radville and input them as priors and Orbitize. And that way you could already start off better. And so she was talking about that, and you can do that. You can change, you can change the priors very easily here. For example, here in the eccentricity, she was able to change the prior from a uniform prior to a Gaussian prior, very simple here. I need to forget. Yeah, if I forget to like zoom in, let me know. Yes, we can see here that it's very simple to change the prior. So that's all. It's not a lot. I'm not going to go over in detail about this notebook, but it just basically works. And here's just showing that when you run OFT with the modified prior, it still works. And MCMC too, yeah, you can run MCMC as well. So, yeah. So now we're gonna go to the pretty plots, which is what everyone wants. If we go to the plotting tutorial, so this is the notebook where you get all of the pretty plots. So here we're using Planet E again. For 7 UMA, we run the sampler again for 10,000 orbits. And then we can plot the same plot that we had before, but we can modify it in a lot of ways. Okay, so you can save it as well. This is the way that I save it usually. And so this is the way, if you're using if you're saving the s dot results way that I had talked at the beginning, which is the same way that it's saved here, this is the best way to load it back up. And then once you load it back up, you can use my results dot whatever you like. You post, I believe, has the likelihood values. And then you can also access all of the orbits as well. And so it has more information. Like if you only want the orbits, you can do it the other way. But if you want all of the information just at once, you don't have to worry about it. You can just save the results in this way. And this is the best way to load them back up. So we can have the corner plot. We can modify the corner plots as well. And so here are the parameters explained. And so we can choose which parameters we plot. We can also choose the range as well, which is nice. If you want to look at a specific range in the corner plot here, you can zoom into that. And then you can also just plot one if you want to just plot one. And then here you can also change the labels. There's very simple things, but it's nice that they're already like facilitated for us. You know, that it's not too complicated to get labels or to get something like that working. You can do it all from the Orbitize package. You don't need to go find some other package to like visualize this and try to fix it. So it's very all well contained and documented. And so if you want to overplot the truth values, well, if you calculate the median and you want to plot only the 95% range, then you can do this. You can specify the range and the truths, and it'll plot, and you can actually see the median for each parameter. And it'll also plot for the 95% range. So that's really nice if you can do that. And you can do any of the other things that I had said before with this. If you want to just have like one of them and zoom in on it, you can also do that. And so now we have the orbit plot. Again, don't run the start MJD because it's gonna freak out. If you also want to save it, you can uncomment this section. But here we can see that it plots 100 orbits. We can see here the separation angle and the separation and the position angle. And then we can customize it as we want. We can let it be a rectangular plot instead of being a square plot. If you just want it to not be constrained to a square. You can also take away the color bar if you like. You can also change the colors of the parameters, which is really nice. And then you can also choose, again, like I mentioned before, you can choose how many orbits you want it to plot. And you can also choose the number of epochs you want to plot. If you want to visualize how it does for only a couple, like how it is for a couple of epochs. Stop me if I'm going too fast. Is there something? Are there any questions?
Yeah. Let's see where I'm gonna get that. All right, never mind.
And you can put a title above it, which is nice. You can just use this. And then you can also put it just to 1, which is nice. And then you can also name the here add add the X and Y axes for the orbits plot. And then we can also modify, we can put markers that it shows where the center of where the star is, which is helpful. Which is really nice right here.
Do you get like a polygon?
Oh.
in your orbits?
Oh, that's for, yeah, that's okay, because that's just plotting, you're choosing how many epochs you want.
Got it,
Yeah,
okay.
plot, yeah. The next one shouldn't be so jagged. And so here, oh yeah, this one I have to, with the error bars and the epochs, the last cell, there's an error. Or is there an error? Actually, wait, hold on. Oh yeah, so it plots this one, but there's an error here, and again, it has to do with the star MJD and the epoch, so I have to ask them about that. But yes, sorry that was very quick, but if anyone has any questions about the plotting in Orbitize.
So I just take this opportunity to say that they're gonna have a coffee break now for the ones that want coffee or and then we have about an hour for lunch after the coffee break, and we are going to do the star shade probably because Sergi just woke up in California and he's going to be online.
Okay.
So I'd suggest that we do the star shade, and later in the afternoon we it's going to be free. You do Orbitize if you want.
Could we do possibly, do we have time to do anything with Radval? Because I know you had a Radval tutorial.
Yeah, so
that
we're
would be
gonna
really
do
great.
it. We're gonna do it before. So after lunch, before we move to the other building, we
Okay.
do the tutorial here.
Okay.
And then when we move to the other building, it's just free for a couple hours and do whatever you want, and ask questions and eventually project on. No, there's no dinner.
No dinner here, so.
There's a coffee again at 3 over there.
Is that possible for us to have an overview? Because I think this 2 days is very packed. We learn a lot. There are so many notebooks. I kind of vaguely get every notebook's function, but it's too much, especially today. The orbits. I feel they are all fitting the orbits. What's the difference? So
what I plan to do is, so we're gonna get the recording, the video of this. It's not really high res, but together with the notebook and the presentation, if I remove like the parts where nothing is happening, that's something you can go back to.
Yeah, I think we will go back to know the detail, but I think 5 minutes to spend on like a 2 block, like day one.
It's a refresher.
We covered signal detection.
We got it.
So we have this package and this notebook doing what? And day 2, we fit orbit in, and we use this package, and each notebook did what?
Yes.
So this is what I
want. Yeah, you want to go back and have like a
I'd
summary.
like to, I think, I don't know, Neil, would you be willing to do that? Because I feel like it would be a good summary.
So what we could do maybe is like, okay, take the agenda and expand, put some links to the box folder for each thing and description of what we did. Maybe something like that. Would that help?
I think so. Just a simple tree plot.
Good suggestion.
Things will help a
Yeah,
lot.
and you're right. I mean, this would help also eventual participants that haven't participated to our events, because we want to sort of put everyone on the same level, let's say, but it's not easy.
But just like even right now, I can give you my vision of it, which is that we described the data in general. Then we described some source extraction tools, VIP, which I don't think any of us actually got working. Did anybody actually get that really working? Well,
No,
so maybe that's something to keep discussing because we'll keep having regular telecons for people who are in the data challenge and we can help each other through Slack and whatever. And then we talked about, what came after that? What did we do yesterday? We had VIP, the source extraction and astrometry.
No, so we had how to
Why?
read the data.
No.
Like,
parallax?
Oh, yeah.
I think that was it.
Proper motion
there
and
was
parallax, we
proper motion,
talked about. So, and orbitizes the orbit fitting. We'll talk about how to fold in the radial velocity data when we do a RADFOL tutorial today, and then we'll show the star shape data. So that's kind of like the super rough arc of the story here, but I think it's good to repeat, and then at the end, we'll just sort of summarize again, like because I agree with you. It's good to just like keep saying what we're doing as we go through.
Guys, I mean, this is a very good tutorial for many aspects for exoplanets.
Yeah, I think this covers a lot of ground, but it's right. It's true. You can get confused as we're immersed in all the details and kind of losing the forest for all the trees here.
I mean,
yeah.
I would think that nothing is like too difficult or too complicated, but it's a lot of different things. And it's true that if we, without like starting points like that, it would be hard to do the challenge in more amount of time, I guess.
For the challenge in particular, like I think what I'm having to do is like what order do we, like what data are we getting and what is like, do we do RADFOL first before orbitize, like kind of like how, or is that part of the challenge?
That's up to you.
Yeah.
Because you'll get all this data. We'll give you up front the radial velocity data and the first epochs of actually all 4 epochs for the chronograph, right? We'll ask you to return whatever results you can with just radial velocity in the first 2 epochs, plus radial velocity and all the chronograph epochs. Then in November, we'll give you the star shade data. We don't give that up front because it's almost like, here's the answer, the star shade is so powerful.
Oh, right.
Well, actually, everything is kind of powerful in its own way.
Everything is, yeah. No, it's true.
It's a good question you asked. I think, if you have something I think you can do a first pass with RADVEL just to see if there's anything obvious with RV. Okay, that's okay, you put that somewhere. That's an information. And then you look at the HLC data, imaging data, first couple epochs, just to see if there's anything obvious in imaging. And then you put that somewhere, and then you can go back and do things a bit more, like, okay, what's my photometry, what's my astrometry, and then do orbitize on whatever I have. I think it's kind of iterative like that. So basically for the challenge, we're going to give basic points to like basic stuff like you identify object 1, okay, and you make a mistake, it's not a star or something. And then we're going to put more points to like maybe like how accurate and complete the exoplanet system you find is, So some people might actually confuse epochs between different objects and get some weird things too, and that would be incorrect, even though orbitize would tell you, oh, that's a nice orbit. I don't know. So we leave that, and then you have you're gonna see with the star shade, you also have some, well, not just with the star shade, you also have contamination from the exozodiacal light, which means that your photometry, your first pass on the photometry is probably not that great. So once you kind of figure out the system, if you want to go a bit further, you can try to correct for that. That's, that's why there are a lot of things to learn, but not everyone might go as far in all the tracks, let's say, and that's why it's interesting. We may have more than one winner in that thing. So if you're really interested by this you know, exozodiacal light correction and characterization, why not? You know? Why not push on that, you know, and maybe forget one thing, learn something else, you know? It's a little bit up to you and the teams, and I think there's no shame in not providing all the complete thing, you know. It's more about learning for both the participants and for us, you know, because we get a lot of feedback.
That's not like reading it in a data set or anything.
I do have a question about the zodiacal dust. Perhaps even in one of, we can maybe focus on one of the simulations that we do already have. If there are multiple planets that are in the system, is the zodiacal dust reflecting motion resonances from just one planet, or do you guys have a multi-planet simulation for the dust environment?
I don't have to say that.
Sort of. Well, I'm just asking. I'm asking, like, just even for these, because that.
You showed one image yesterday.
Yeah.
That showed, I think, two. Was it two?
Of the dust.
Yeah, but it's only one planet's gravity in that simulation.
Okay.
Okay, so
I wasn't
so I didn't know
sure
that.
if we could say or if it was like giving away or.
No, because that's
Okay. Yeah, it's only one
really
planet.
our
Yeah.
We don't have those. We don't have enough customized.
Those don't exist.
Dynamical simulations.
Who has them? Because I would.
It's
Yeah.
Yeah,
So only
let's
one
say-
planet. Yeah.
Okay, let's say first order, it's just a contaminant. And the main goal of the challenge is to derive the orbital parameters of at least one planet. But you know, if someone is interested in, like, also saying like, oh, that's the number of, you know, that's the Zodi level I get or whatever, that's interesting. You know, that's something that is going to be useful. You know? Or do you provide that? No, you don't.
Provide
the actual level. So
well, the Zodi is a surface brightness unit in the end of the day, right?
Yeah,
it's not going to tell you like the mass of dust in the system. There's no easy extraction.
Yeah.
That's why I would rather keep it simple.
Yeah.
So let's say also a general thing. It's not too complicated. You know, it's not like too complicated.
To follow up on this discussion, so it's okay for us to just participate in part of the competition, right? For me, just want to apply on my own method on a star-shaped image and extract the
I mean,
planets.
it's great. I mean, it's great because then you might be maybe the person that go furthest on, you know, on that topic, you know.
It's an
you might not
interesting
win the
question.
whole star shape,
Yeah.
the whole challenge, but you know, that's interesting, you know, and that maybe it's interesting for you too, you know.
If you're trying to do the most complete job and win the data challenge, like then you know, do the whole thing. But if there's something that you're interested in and want to push on, that could result in a good publication for you and a really valuable contribution.
Yeah, I mean,
So
in the end, that could be
do
more
it.
valuable than the honor, whatever it is. You
Yeah.
don't have $1 million.
But
You don't have like a 5-year
900
fellowship.
shares of Amazon.com.
But the success metric will be the orbit fit, and the star shade alone is not going to necessarily get you all the way there.
I think I'm fine with that.
Okay.
Okay, should I finish up?
Yeah, I think we should break. Do you
Yeah,
have?
this is the last one.
Okay.
Yeah. Well, real quick, this notebook you can just run and you can visualize an orbit. You can look at also the RV, and you can these are sliders, so you can modify yourself and you can just see how it behaves. Just a fun little visualization tool, which is pretty cool. So yeah, so you can play around with that. the notebook is there. And then, so to finish off, which is what we want from all of you when you're in the last steps of the data challenge, you want to submit your results. This is just a quick notebook to show how to load back your data, and then also how to it's just a quick little notebook to get the median and to get the 65, like the 1 sigma on each parameter, and then submit that for the data challenge for the planet that you're looking at. And again, you could run this various times. If you find more than one planet, then you would have several of these. But this here, we're loading in the results from planet E, I believe, and it'll obviously specify better than this, so you can know which planet it is. And then we would determine the median and the 1 sigma of all of the parameters, of all of the A parameters for all of the 10,000 orbits or however many orbits you decide to run. And so here we can also visualize them, and we can also plot. You can also plot the median. It can also, if you want. Do they have flexibility on what they submit? Like if they want to submit like these plots or something, as well as the values, or?
We have to think of it deeper about it.
Okay.
I think yes.
Okay, because if they want, they can. Yeah.
But I mean, it's not like it's mandatory, because
Right.
what really counts is like what your bars are, and like we're gonna make more like a table
Yeah.
of the results.
Yes. So actually, so the table is right here.
But you know, anything is interesting if it's useful.
Yeah, I guess it's just like an easy way to visualize it, I guess. I just thought that I would share this with you all, and you would have it handy for when you get there. But yeah, you can change. So I should have documented this better, but this is for 1 sigma. You can change it if you want to do 95%, like 2 sigma, or if you want to do something else. But then you can also, and then this just plots it and plots the median for these parameters. You can also, this is also not design. This is wrong. That's in radians, by the way. And so, yeah, this is just to visualize the values that you got, for you to see, and see if you need to run more so that it converges better or something. And then this is just a quick way to save your orbital solutions, and it will output a table. So it will output a table that looks like this. How can I? Or maybe not. Okay, all right. Can do things. But yes, it just saves all of the A parameters, and it also saves the best fit orbit. So it has the one with the lowest chi-square. And you can compare it as well with the median for each parameter and the confidence range. And you can change this as you like, but maybe this is something that you would look for as an input, as a kind of like an end result, like, oh, this is the semi-major axis of the planet, different orbital parameters. So maybe something like this, yeah.
It's interesting that actually the median outperforms best fit. I'm comparing truth to what we. It's
interesting. So it's always good to I always like to look at the best fit orbit. Again, this is for 10,000 orbits. Maybe it's better to run it for more. Maybe the best fit is better.
Yeah. So for reference, the true semi-major axis was 10.0 AU, 10.25 median.
Yeah.
And
so it got pretty close with only 2 epochs. So this was for Planet E for 2 epochs, and the true value was 10 AU, and the median here was 10.2, and 10 is within the confidence range. So.
How are you displaying this table right now?
Oh, I just I just clicked on it.
Okay.
Yeah, I just opened it with.
Okay, so we should.
Sorry, yeah, I
we
didn't
should
use.
break because otherwise we have less
Yeah,
than an hour. So.
Great.
It's always-
But yes, this is.
Thank you.
Thank
Yeah,
you.
thank you for all of that. That's really great.
So I think we're gonna start. Thank you. Thank you very much.
Sorry about that.
So, okay, is 20 minutes okay for you?
Yeah, I mean, I will adjust it. Yeah, thank you so much. Well, hello, everybody. And again, thank you for your questions. I'm Sergi Hildebrand, and I will be talking about the Starshade imaging simulation that we have prepared for the data challenge. So if we go to the next slide, we will show a movie of how the concept of the Starshade and a telescope work. So maybe you can click on.
We're looking at it.
Yeah, thank you so much. So on the left-hand side, you can see the Starshade and the petals are unfolding. And once they are unfold, you'll see how the Starshade is positioned in the line of sight between the telescope and a target star. And in that way, you'll see how the light of the star gets blocked by the Starshade, and it's suppressing it by a factor of about 10 to the minus 10. Let's see that. So here we have the Starshade, and it's blocking the target star light. And we have this suppression of 10 to the minus 10. And then the light of the exoplanets, which is reflected light from the host star, gets into the telescope without practically any change.
What happened?
Unless the exoplanets are too close to the Starshade. Now, this picture is quite optimistic because, for instance, one of the things that you can see is that in this movie, we could see features of the atmosphere of the planets. That's completely impossible. Is for a target like the one that we are considering, we would need a telescope whose diameter would be 30 kilometers at least, and well, that's not going to happen. And also, we can see the petals; they are resolved, and that only happens for a telescope that is at least 30 to 40 meters in diameter. But at least the movie shows the main idea that the Starshade is an external occulter that blocks the light of the host star and allows the nearby reflected light from the exoplanets to arrive to the telescope almost without any change, unless they are very close to the petals or inside. So we can go to the next slide, and we will start to show something more realistic. So here is a schematic, a cartoon for the case of WFIRST. The Starshade in this case is about 26 meters in diameter. And the separation between the telescope and the Starshade is pretty big. It is about 30,000 kilometers. And that's in order to only block the light of the host star while keeping the light of the nearby exoplanets to come through almost without any change. So for instance, you can see what we call the inner working angle, which is just the geometric angle from the telescope to the tips of the petals. And you can see for the blue band that we're considering for this data challenge, it is 72 milliards seconds only, which corresponds to the distance approximately of the target that we are considering today at about 1 AU. So a planet that would be 1 AU away from 47 Ursa Majoris would just fall on top of the edge of the petal. And that's one of the good things about the Starshade. Now, the Starshade, it has some disadvantages. One of them is that for every target that we would like to study, we need to retarget it. We need to reposition all the Starshade, and then it consumes fuel from its own thrusters. So in summary, since we don't have much time, but just to let you know, the lifespan of a Starshade mission is usually considered to be 2 years because of that, unless there is some refueling, but it's pretty hard, and allows one to observe like about 35 targets for 2 weeks each. This is an average. Some targets will require more, some targets will require less. But it takes about a week or sometimes more or a little bit less to retarget the Starshade and position it into a place where the suppression really works well. So that's one of the disadvantages. The advantage, the greatest advantage is that there is much less loss in the optical throughput, and about 1 order of magnitude more photons arrive to the detector compared to an internal occulter, which is the same model. So the idea of the Starshade would be to follow up observations that have been very interesting with WFIRST and the coronavirus in order to get, for instance, the spectra because of the highest throughput. Okay, if we move to the next slide, I will show you how we generated these simulations. So in order to really take into account a realistic scenario where we have the diffraction of the light rays through the star shade and the petals, and also the star shade may be spinning, we use this tool, which is called Sister, which is a versatile tool designed to provide enough accuracy and variety for the star shade astrophysical simulations. And it's an open source project written in MATLAB, and you can find it in this website. At the bottom, you can see the co-authors of the tool. And well, you're very welcome to look at. You don't need to learn about it. So if we go to the next slide, but it might be interesting for some of you to know that there is this software that is, it has a previously documented handbook, and there's plenty of examples. And if you would like to study with some more detail, the performance of an STAR solution, then you can use it. And that's the way we generated our simulations using this software. Okay, thank you. Let's move on. Thank you, Julian. So that's just an example of how the optics works. If we are at the very center and we have an ideal star shade and the star is properly aligned with the star shade, then we see the first image on the left-hand side. Yeah, thank you. And you can see all those rings, which are area rings. That's the Arago spot. You know, as you will know by electromagnetism, if you block a light, kind of miraculously, there is light at the very center. So you don't block it at the very center of the spot. And the design of the petals, the fact that they are not just a circle, that they have this kind of flower shape, is done in order to minimize that light that leaves to the center. And that's what's going to survive from the start. And we can see that in this case, you know, the peak of it is 2 to the minus 11, which is a lot of suppression, but that's for an ideal star shade. If we move a little bit farther from the star shade, the response starts to look a little bit more weird. And then eventually, as Julian was pointing out, we arrive to the regime where the star shade does not perturb the optics of the system. So on the rightmost image, we have the response of the WFIRST PSF, the pure telescope light, well, without a coronagraph. It's just directly going through the pupil and then to the detector. Now, even at some distances like the petals, you can see that the PSF is very symmetric, but there is some suppression. There's a 7% suppression. And at the bottom, I just plotted the transmission. So how much light gets suppressed depending on the distance. And well, if a planet falls into the shade, then it will be suppressed. So we don't expect to do science there. And that's why the design was 1 AU at the petals, because we don't expect to study planets that are closer to 1 AU, for instance, that host star. Okay, so if we go to the next slide, that's a little bit how the simulation is built up. We start with the starlight, as we were just showing before. We multiply by the whole flux of the star at each wavelength, and we integrate across the bandpass that we have. And then we introduce, for instance, some telescope non-idealities, like in this case, the jitter of the WFIRST telescope. It could be 20, 14, 15 milliseconds, depending on the specification. But it's just, you know, some error in the pointing of the telescope, not the star shape itself. And then what we do in this data challenge, because we want to be more realistic, we don't consider an ideal star shape, but we have introduced a perturbed and non-ideal star shape that corresponds to the specifications of the WFIRST mission. And you can see that it's much brighter. There's much more starlight coming out, not only at the center, but everywhere around. So that's more worrisome. That's right, that's the third image. Thank you, Julian. And then what I will do now is to divide by 100. So it's about 100 more starlight that goes through with a non-ideal star shape than with an ideal one. And I will divide it by 100 because we are going to add other effects, and those effects are of the same order, and otherwise we're going to saturate the image. So let's add the next worrisome effect besides the starlight. The next one that is only characteristic of the star shape, yes, please, let's move to the next slide. Thank you, Julian. Is what is at the bottom row called the solar glint. So, well, the star shade, even though it's painted in black and it tries not to absorb all the light that comes to it from the sun and not reflected, the petals, the shape of the petals, no matter what we do, they will diffract some of that light, and a little bit of that light will get into the telescope. The sun is its apparent magnitude at L2, of course, is minus 26.74. So it's a lot of light that goes through. So even though we have like, you know, several orders of magnitude of attenuation, it's competing with the light of the star, of the host star that we are blocking. And that's called the solar gleam. So it depends on the relative position of the sun, the starshade, and the telescope. And we can know that during the mission very well. And we also expect that we can measure that pattern to some good extent during the mission, especially if the system is very interesting. We would just move the telescope and the starshade a little bit far away, and the star would not be blocked, but at some arc seconds, the starlight would not, you know, influence the image, and we could take 12 hours or 24 hours of that solar gleam and use it to subtract, or other ideas that we are right now exploring in the starshade technology development. So if we add the solar gleam and the starlight that remains, that's the last image at the bottom, you can see that there is a big bright spot at the center, and that's where we have to compete with. These are instrumental effects. Now, if we add the planets, the background field, noise, the exozodiacal light, then what we get is an image like the following one that is representative. Yeah, we can change to the next slide, please. So this is representative of the data challenge. These planets are not the ones that you have to find and study. It's for another orbital configuration, but the exozodiacal light is what you will have. And it is 5 times as bright as the solar system with a different distribution. That's right, that's it was a very beautiful and realistic image of an exozodiacal light that might happen. You can see that there is kind of a dark ring at the center, and that dark ring at the center is not just the starshade blocking its light. There is an effect of some planet there that is doing something. And well, one of the planets, planet B, is clearly seen in this image, but the other ones are kind of on top of the exozodiacal light. So depending on the phase and the distance of the planets and so on, it will be easier or harder to detect them. And that's what the challenge is about. So you will get some information from the coronagraph images. You will get some positions of the planets, and with them you may estimate orbits. And maybe you can even predict kind of where it might be in the next epoch when we observe with the starshade. So that might help you find those that are fainter. Now, in order to deal with the interior region, where some planet might be closer to the star, then we have the starlight and the solar gleam, and of course the exozodiacal light. So regarding that, regarding instrumental effects, we will provide you with a solar gleam template, a noisy solar gleam template, like is representative of what can be measured during the mission. And that's the next slide, which is the last one. So I really encourage you to use that, because that's something that we expect, you know, to do a good job during the mission. So you can subtract it, and then what you see, it remains, you know, the starlight, which is the non-ideal one. That's right, thank you. And that's kind of, you know, it gets to 1 AU. We could also subtract that with a template, but I think that it won't be necessary for the data challenge.
So Sergio, I'm just going to blink back and forth.
Yes, please.
Between the previous one,
right,
this one.
Julian, yeah, that's very good. So, for instance, you can see that the solar gleam has apparently 2 big lobes on the left, on the right-hand side. That's, you know, where the sun, you know, is diffracting more, and then it's combined with the PSS of the telescope. But it helps. If there would be a planet close, right now you don't see any planet because there is no planet there. But maybe in the data challenge, I don't know, you have to check. Maybe there is something when you subtract the solar gleam, and that will help for sure. The solar gleam has noise, so the subtraction is noisy. So we try to be as realistic as possible. And well, you can see that now we don't know where the planets C and D are. So there will be a little bit of, you know, source finding and matching in the real data challenge. The nice thing is that you can see the structure of the exosolid pretty well. So you may even use that information, you know, back to the CGI images, or try to find a template for the exozodiacal light iteratively to find any other planet. But that's going to be probably challenging. And that's probably how life is, and that's what we would like you to let us know, how much can be gotten from this data. And I think that's it. You know, there is a last slide that just says, you know, have a great meeting. And what we will also share, sorry, I forgot to say that, is the PSF. the PSF, even though it changes, especially for the planets that we are considering, we can consider that PSF is not, we are not inside the petals of the star shade. So you can use that in order to find centroids or to estimate the photometry. And it should be relatively easy. We will show when we release this data in mid-November another tutorial with an example of how to use it. But basically, you can see you would simply match the PSF, you know, maybe with some software or yes, with a Fourier transform around the planets, because it's where the PSF is especially invariant, and you would find a pretty good centroid. And well, that's all what we wanted to show so far, just to, you know, get some idea of what you may find in mid-November that may boost your planet finding.
Thanks a lot, Sergi. We're gonna go for questions. Yeah.
I think I'm good. I have
you're
heard
good,
this presentation for 3 times.
So it just so happens that in that particular example, the other two planets are being hidden by the structure of the exozodi. How deeply do we need to be able to sort of predict the way that the exozodi is going to be reflecting from inferred, like, inclination and stuff? Because I know nothing about doing that, so.
So that's a general question, and I think that the answer is that we would like this exercise to show, you know, what's necessary in terms of tools and algorithms to get to the data, right? If we find that no one is ready to extract them from the exozodi, and maybe it's impossible or maybe not, then we would need to, you know, to call for more attention into those kind of tools.
I would say also, it's not necessarily just the exozodi, you know, as Neil showed, for some epochs, the planets are not as bright, right? And so it may be that for some bad luck, a planet at the time of the starshade epoch was not bright. Okay, and so that's why also, like, general rule, like HLC, RV, and starshade, they all have their parameter space. And the time is, you know, the epochs and the time is also another one, the position on the phase curve. So, you know, it's not necessarily just the exozodi masking those planets in this case. So it's it's a bit complex in this case. I would say, you know, there's nothing much you can do if you don't see them in this. If you don't have prior knowledge here, you just say, I don't see them, right? And not use the starshade for this, not use this epoch basically for this particular planet. You know?
I don't know, we may find ideas, you know, this is an image that has a linear scale, and therefore, you know, maybe by eye we don't see it, that if we would like, for instance, for outliers, it could be, of course, noise spikes, but if we would look for outliers and then try to find where those outliers has a spread that is compatible with the PSF size, and one could conclude that that is you know, an object that has been compared.
Yeah, also another thing is, like, if you progress in the data challenge and it makes sense because you have other epochs that you expect some planet to be here, then maybe you could, like, do some kind of post-processing, or you know, try to do better than just a simple subtraction, to, you know, try to see if you can detect them in this image. But that's, you know, that's what we would do in real life, I think. You know, like if you have like this kind of data and you suspect there's something, you know.
Right, and notice that this exozodiacal light is very well constructed, because for the first time we are considering one that changes also in time. So we cannot average the exozodiacal light from different epochs and say that's the exozodiacal light. So it also changes in time. And as Julian is saying, that's kind of real life. So we want to know in advance when we need to develop.
I don't know. Maybe also you could like do a noiseless model or something to subtract without propagating more noise or something, but I don't know. This is maybe beyond the scope of what we are trying to achieve.
Right.
There's another question, sorry.
So the exozodi are co-orbiting?
Yes, I think so, right?
Yeah.
They orbit.
Yeah, so it's not like fixed yet. What's the other questions?
So anything bigger than diffraction limited PSF, like exoplanet size, that is exozodiacal?
Sorry, I didn't get your question.
Anything which is bigger than PSF of exoplanet, that is exozodiacal? How do you define?
No, I mean you could have an extragalactic galaxy somewhere also. Or, we don't see anything here, but you know you could have.
How do you?
They are in the image, but we don't see them in this scale, right?
Yeah, I mean if it's right in the middle and it's an elliptical galaxy, that's going to be complicated, you know. But if it's you know, hopefully it's not the case. And also I want to say, you know, if you look, so on the website, I put links to the box folder of previous hackathons. And if you go to the second hackathon, the one we had in June in Pasadena, in this case, the configuration had 4 planets. And it was really easy to see them on the star shade. So the case that Sergi is showing here, it's a bit different because we have, you know, obviously some planets that are not that easy to see in the star shade. So, you know, it's just to show that there are different things that are possible. The configuration of the data that we release on Sundays is different.
One question, how do you differentiate between exozodiacal dust and exoplanet?
And we don't have it. We have only one filter, yeah, 2 filters actually. Well, one is diffused and extended, the other is diffraction limited, but
exozodiacal cannot be same size as an exoplanet?
Well, I mean, you can have some weird effects, right? I mean,
well,
especially if you convolve with the PSF and then you. So I'm not expert in that, but you know, I would say that if you use really aggressive post processing, you may start to create all kinds of stuff. You know, so you have to.
So well, the question is
separate things, you know.
I think that the question is a very good one, by the way, because if you look at the bottom part of the exozodiacal line, yeah, thank you, Julian. That's almost the same size like the exoplanet, right? I mean, the angular
we
size.
see better on this screen here.
So it's very similar to the exoplanet. So that's right. And so there might be, so the reason, for instance, for that, well, maybe looking at other epochs, and then you may see, you know, that blob that looks here like a planet will not look the same in the next epoch. So right now, it might be more extended in the next one. So you would have a planet that, you know, that would become bigger and smaller. So you can discard that and consider it an exozode. But only with this image is true that the bottom part of the exozodiacal line could almost mimic an exoplanet. We don't have a spectroscopy here and so on. So yeah, but that's why we have different epochs.
I mean, that's why also it's going to be hard, you know, to do science with the WFIRST, even if it flies, even if it works, even if you have a star shade, you know.
Right.
It's, we should move on. So,
did you say that there would be 2 filters?
The star shade bandpass is different from the HLC bandpass.
And there are slightly different filters on the
data
star shade, right?
challenge, this doesn't matter, right? Or does it?
It didn't matter for the exozodiacal light simulations. I definitely took that into account.
Yeah, so there's a different flux
That's the only thing.
scattered back from any source. So we have actual
Okay.
some wavelength dependence between those two band passes. But.
Yeah, so I believe like the way the instrument is planned, there will be 3 different filters, but close to each other or something like that for Starshade. Not an expert on
actually,
that.
Well, doesn't matter for this. We're only doing 1 band pass.
Only, so our data's in 1 band
One
pass,
band
and we
pass
get
for each instrument.
reference frames for in that band pass as well, I guess.
Yeah, that's not the competition I'm looking for, sorry about that. So yeah, I was gonna show. Yeah, so I think if you look at that, forget about the IFS. I think so. Those filters that say like Starshade filters, are those still planned or something? So I assume it's like 1A, 1B, 1C to be close to each other. Or, actually,
No, those are engineering filters
okay.
for wavefront control.
Okay, so it's not okay. Engineering control. Yeah,
There are red. There are filters for the Starshade that are at redder wavelengths. We're showing
well,
a blue
right
band
now,
pass.
because of the scope of the IFS, the rendezvous mission, the Starshade plus WFIRST, is being redefined as we speak. So the final set of filters is not defined. So we expect to have this, this one, and then a green one, which is green-red one, 615 to 800 nanometers. But the conversations are just happening this week, and will follow up in the next weeks. So we will release this data if we think it's worth it to release at a different wavelength. I don't think that by mid-November this conversation will be closed. So we probably will assume that we have this blue band filter for the Starshade.
I have a question. Maybe it's, I don't know. So I don't understand this in the context of VIP. Is it done after, like in terms of image processing, like how exactly, or independently?
Okay, so imagine you do your VIP or whatever on the HLC epochs, and you have 4 of them. And then you get 2 epochs of the Starshade, and you just do it again, except your model PSF in this case is the one that shown here.
Okay, so it's
yeah, exactly. You do it independently, and you do your astrometry, your photometry on, let's say, this is your planet you're trying to characterize. Do this one, and then you make your little table for orbitize, eventually to use everything or just the HLC, depending on the picture we're at.
Can I use the same PSF for the first 4 epochs and do a comparison?
Yeah. Yes, except you saw the PSF is field dependent because of the and so you might, if you want to do something a bit fine, I mean, at first you can maybe use the same PSF, you can use a Gaussian or something to get a first pass, but then you want to use eventually the PSF that has the right shape to be as precise as possible in astrometry. Yeah.
I saw a contrast curve on your other presentation. Can you? Does it show like
on the one I just?
Yeah, I saw it.
Yeah,
does it have the star shade?
So Neil had it in his presentation yesterday, but didn't show everything, and I forgot to include it, so I included it after.
Yeah,
so it's the generic thing you see a little bit everywhere. And so this is kind of comparing the ground-based instruments, WST here. So this is the wavelength, the separation. But so that's kind of like, this is one Jupiter at 10 parsec and one Earth at 10 parsec. So visible. Sorry, it's not wavelength. It's separation, but you know, under D, so you can sort of think this is reflected light. This is reflected light, and this is emission.
Yeah, those ground-based ones are operating in the infrared.
So like you have blue and red, basically.
So they're going after planets that are self-luminous because they're young and giant and emitting a lot of light.
So this is kind of like the best ever achieved with Sphere on Sirius, you know. So brightest star. Some of the best maybe achieved with GPI, so it's similar, about 10 to minus 6, 10 to minus 7. We think that JWST would be, you know, competitive at larger separation. It's going to be starting to win there. This is where NICMOS was. This is Magellan. Let's see what else. Here, the visible adaptive optics of Magellan is somewhere here. So you see, I mean, we're talking about a different contrast regime completely. You know, like it's really several orders of magnitudes. And this is the requirement. We don't have any science requirements anymore for the tech demo, but we still have like a, you know, if we don't achieve this, there will be kind of a bit of a failure. But we think that if we do everything well and things go well, we may actually achieve this, you know, which is kind of like the previous requirement when it used to be a science instrument. So that kind of relaxes. But so we think that the contrast will be somewhere in between these two lines. And I just highlighted the blue here because that's the mode we're interested in for the data challenge.
In the star shade, it would improve it how much on that?
Yeah, so star shade is a cool new thing because star shade, you can detect planet all the way here, you know. You don't have an outer working angle issue as much as the, so I would say the star shade is probably below and going further. But then it's not going to do a whole lot of targets, right? So it's also a bit tech demo, which is necessary if you want to do HABEX one day.
So yeah, where would HABEX and LUVOIR be on here?
Yeah, we
down below the Earth at 10 parsecs.
Yeah, so HABEX and LUVOIR, they want to image directly several of those.
Yeah, that's what they're
So
going.
you need to be here.
Stepping stone.
And then the whole debate is like, how many of those can you access? You know.
Yeah, and the performance, there's a lot of, like for HABEX, where you would have a star shade with like a 4-meter class telescope. There's so many variables that go into it because it depends on how much power you have, you know, how much fuel you have for moving the star shade around, how many star shades you have, what the prevalence of Earths actually is around in the HAB zones of stars to tell you how to design that mission to actually have a high probability of finding, you know, X number of Earths. So there's a ton of engineering things and then a ton of astrophysical parameters that have high uncertainties, and you have to be pessimistic about all of it. Like how many exozodies are typically around stars that have planets, etc. All folds into the mission design.
But this is not final. This is constantly evolving depending on, you know, the reviews and the things that change a little bit. For example, I think this was done for the IFS, which is not going to happen. So the spectroscopy is going to be a slit spectroscopy. I don't know what the sensitivity would be, but maybe it would be kind of similar. Yeah, so, but you can tell it's true just by looking at this, like the whole excitement of getting this flying in this decade, right? Even though it's probably not going to be hundreds and hundreds of targets that you can look at. You have to choose wisely.
Star shade limits the number of targets?
Yes, because you have to slew, you know, the whole star shade So you could imagine, you know, like WFIRST is doing something else in the meantime.
It takes like about 10 days to move from target to target for the star shade if you have like a few dozen really good
So the
stars.
star shade has to move, you know, and telescope has to slow, but in the meantime, telescope can do wide field survey, micro lensing, whatever.
It's been sold as a perk to the mission that it can do general astrophysics, and it will share, you know, general astrophysics with a deep planet search. But if you did have more than one star shade, you could optimize for different wavelength regimes, have star shades at different distances, and really ramp up the efficiency of your search and characterization program and use a lot more of the mission just for exoplanets if you.
So we really have to go to lunch now. So thank you, Sergi.
Okay, so we're gonna do this Radmel tutorial now. The installation is not hard, but there is this one snafu. You need to make sure you don't use the very latest installation of MC, the MC code. So before you try to install Radvel, first install this old version of MC. But if you already have tried to install, then uninstall it. So you can do, if you've already installed import's okay, but if it was the latest version, it's gonna break when we do certain things.
So should we just, even if it did import okay, maybe we should reinstall?
Yeah, so I recommend just these two commands. So uninstall the MC that you have.
But if I use Anaconda?
It will find it.
Well, I'm actually curious if that affects replies or my.
It could, but we'll live.
Okay, all right.
It won't. I think it should still work.
If I were to check which version of MC I have at the moment, how would
Should
I
we make it
do
a
it?
different environment?
It's probably,
Yesterday,
if you
import it, it's probably MC dot _ version
We can try Python M route or MC and then.
Okay, so I can show you how you can check a version.
Actually, yeah.
So if I do this, import MC, MC version. Okay, great. Run.
Okay, let me check.
That's not so bad.
That helps a lot.
Worried now.
Okay, so then you can go ahead and do pip install Radvel if you haven't done that already.
How's that? Okay, so you need to do pip uninstall Radvel, right? And then
Pip uninstall MC.
they have Radvel, but not MC.
It would have installed in the background, so you're probably okay.
Probably okay. All right. Where is the problem? Who does have the problem? Anybody who?
I'm gonna check right now if I have.
MC and then Radvel, or?
When I installed 2 days ago, I encountered a version conflict.
Okay.
With this, and I contacted the Radvel people, and they told me they weren't ready for MC 3.0 yet.
So I have Radvel, but I didn't install MC.
It does in the background.
When you install it, like installs other packages.
When you install Radvel, it installs other. When I do which EMC, it doesn't come back with anything.
Not necessarily. But this is, so I recommend when you get to you can check the version.
Are there 2 things to download from the box?
There are, so there is.
It's too thicker.
Yeah. There's a file called Radvel demo, which Radvel demo, Python notebook, and rv.dat. So you just need those two files.
Can you go back to the line to check the version? Sorry, my bad.
Yeah.
Oh, like the one in the notebook to check the version.
Should be MC dot underscore version. Underscore.
This is it.
Oh, thank you. Okay. Already have it.
Okay, good. They might have fixed it actually within the last day, so that was actually the right one.
Nice.
So the packages suggested here, they are kind of stable, or if we can generate some flowers or data with these packages, referee, when you send a paper to publication, referee accept this kind of packages like Redwheel or Arbit or
Yeah, people prepare publication quality plots with this package. Yeah. But just as general background, because not everyone works on radial velocities, and it's certainly not my area of expertise. I recommend this. It's a general overview paper from 5 years ago. Deborah Fisher is the lead author. If you just Google this document, I'm sure you'll find somewhere in the archive. But it's an overview of all exoplanet detection methods. And it has a really straightforward representation of how radial velocity signal amplitude relates to the m sine I, what we call the mass of the planet multiplied with the sine of the inclination of the orbit, along with the period and the eccentricity are all in this one nice handy expression. And so this is a useful way, once you actually do your analysis of the radial velocities and you come up with an orbital solution, you're going to get a k parameter. And that k parameter is how you're going to back out, the m sine I of that planet. So that's an important question to have in mind, because Radvel is not going to do the interpretation for you of that k value.
Oh, it's going to give you K.
And it's all for k. And then there's an inclination ambiguity because radial velocities only measure line of sight. So
It'll live that paper again.
it's called exoplanet detection. I'll just post it.
Techniques. Okay.
I'll post it on the Slack.
There's lots of other things about other things.
Yeah.
Oh, is this from the exoplanet?
Protostars and
planets?
I typed
It's I think it's from a different. It may not be from a book.
It's the Protostars and Planets conference proceedings article.
Oh, good. Maybe not. Okay, so we've got Radvel installed. Hopefully it imports okay.
You gave me an error, not an error, just I guess a warning or something.
Yeah, some warning about something going out of date.
Numpy.u font size change may indicate binary incompatibility.
So
But I don't know if that's relevant.
bad cop. we have not that much time, so let's not stop on warnings. Let's move on.
Yeah, so we're going to analyze a simulated radial velocity data set that we used in our June CGI PAC event at IPAC. And so this was produced by our colleagues at UC Riverside, Jae-Sing Lee, and his PhD advisor, Stephen Kane, who have been working with us to simulate radial velocities. And so the rv.dat file that you can open up, let's get it.
Did you change the Radville demo today?
Yeah.
Okay, so I'll re-download that because I think I've downloaded it while you're still working on it.
So if you can open rv.dat in any text editor. It's a very simple ASCII table. 3 columns. First column is the date in Julian days. Second column is the velocity, meters per second. And the last column is the error. So part of their simulation is adding noise to that simulation. So we do have different errors over time.
The box, like there's a file day 2, but the box doesn't.
It's notebooks.
Oh, okay.
It's
in notebooks.
Yeah, it should be. I copied it to both places. It's a little confusing, but I just put it in the notebooks directory to make it easier to load, so you don't have to worry about changing path. So hopefully you can, if you've downloaded it, you'll see that it's right in the same directory as your notebook. And you're gonna load it with the package that Janelli warned you not to use with orbitized pandas. I'm actually adapting a notebook that the Radville team has on their GitHub page.
Oh, there's
So
handouts we can't have too. Interesting.
And this command is just a way to get a preview of the table that you loaded. So you see you've got loaded your 3 columns, and we've labeled them date, velocity, and error. There are 190 data points here, and we can just make a quick plot of all that time series.
Nice.
Right away, so there's a pretty strong signal here, right? This is promising, and the way, I haven't learned for a rigorous way to start initializing these models, but I actually just eyeballed the amplitude and the time conjunction time of this planet, of what looked like a big signal. And so I guessed 20. So if you look at just this scale here in meters per second, something on the order of 10 to 20 meters per second. So I just put in 20 meters per second as the initial model. I looked at the period, just going from peak to peak.
Neil, can you just make
everything bigger? Yeah. Sorry, too much. I'll go make this a little bigger.
Yeah, it's gonna add.
How does that look? Right, so you can actually, if you have a strong signal in your radial velocity data, you can actually just look at the distance from peak to peak and use that as a rough estimate for the period of whatever your strongest signal is. And that's what I did here. I set that to 1500 days based on what the actual time span was in that file. And the conjunction time is one of the 0 crossings. If it's a sine wave, it's going to be a 0 crossing as it's going down. And I just assigned it. One of them, I don't think it matters which crossing conjunction time you use, but that's the one I picked up. So 5300, which was right here in the curve. So that's how you initialize a model in Radvel for one planet system. Yeah.
What are those two variables of C code?
Those are specific parameters that it searches that I will have to. There's a square root.
Little omega?
Yeah, it's a square root of each centricity multiplied by the cosine of the argument of periastron, I think. I recommend Benjamin Fulton, who does much of the development of this package, has a paper where he kind of walks through how he does this with a real system. And I'll also make a note to post that onto the Slack for reference. But we're treating those as 0 because first of all, I have no idea how you would even guess what those parameters are, so I set them to 0. And next step is entering a likelihood function. So this is a function that will evaluate a chi-squared against the data. Nothing changing, no new parameters that we're specifying.
TCL is what again?
That's the conjunction time. So it's either superior conjunction or the inferior conjunction of the planet when the planet is either behind or in front of the star.
And you made a guess based on where one of the peaks is, or
a 0, kind of a 0 crossing of that curve. Okay, so next stage is we actually plot what my initial guess was against the data. So the orange curve is my guess, the 20 meter per second amplitude and the offset and the period are there. You can see, there's something weird going on there because this is a multi-planet system, really. So that's why you're seeing an envelope on top of a single sine wave. So let's see how we do with the one planet fit. It's going to run an optimizer to search for best fit parameters. It's not doing an MCMC yet. It's just doing, it's minimizing a cost function in the neighborhood of the parameters we gave it.
Nelder-Mead is the method it's using.
what did you say?
Nelder-Mead in line 19.
Yeah, so this is,
Nelder-Mead.
there are different families of,
Simplex versus Levenberg-Warncourt.
yeah. So there's a whole list of optimizers that are built into this Python library.
Oh, okay.
I didn't have, I didn't really explore them. This is the one that was in the notebook on their GitHub page. So it did actually terminate successfully. I found, in my experience, that I had to increase the number of what they call function evaluations. So there's a parameter that says, if that optimizer is calling your likelihood function more than n times, it's giving up. So that whatever that default was, it was too low for me. So I set that up to 10,000. And that seemed to get it actually terminate successfully. So actually come up now with a one parameter fit, planet fit. And that's the best fit we get, is the red curve. So we're seeing 3 curves now. The orange curve is the initial planet guess, and the red curve is the best fit with one planet. Not that great, right?
I've seen worse.
The period is, I can tell you, is not far off, but the amplitude could be wrong. So what if we try a 2-planet model? We can use the same function we did before with the 1-planet system, we just need to now initialize two planets. And I really did just eyeball again. I guess that the second planet is a weaker signal than the first one. I set it to 10 meters per second amplitude. The period to me, when I was looking at this, I thought, okay, this is going to be, because of the envelope goes down and up, maybe the period is about the length of that whole window we have. So I set it to 7,000 days. And I also made a pretty wild guess for the crossing time. So we need to make a new likelihood function for this system, the two-planet system. Same setup as before. Right, so now we're running the optimizer again already on the two-planet system. And it runs pretty quickly. Again, I set, this is something I changed. I increased the number of function evaluations. And it's gonna merge really well on this particular system. There's a lot of very good measurements in this data set, right? So we're making it kind of easy. There's not a lot of systematic errors. It's kind of just a small random noise on, and these are gas giants. We have a very long time baseline, so that of course helps. So the red curve was actually hard to see. Is our best fit two-planet system.
Alright, what's the, you guys tell us what the orange thing is? 'Cause
The orange was the guess that I put in the beginning.
I see, right, but the guess with two
Yeah,
planets.
so I put it up here.
See, where would that plot show? Oh, here it is.
So it's, the conditions are important.
They are. I mean, I have, to be honest, I haven't experimented with this enough to tell you how far off you could be in each of the parameters. I was actually surprised at how well it did, given I did not have felt like I have a good guess for the second planet. So I was pretty surprised that it's all for it.
What's the error on the data points? It's tiny.
This will, so the optimizer won't give us errors.
No, I
That
mean
will
error
be,
on the RV.
oh yeah, sorry.
It's fitting, 'cause you've
1
got-
meter
you've
and
got
then
tiny, errors.
1 meter up to 20, the year 2020, and then 3 meters.
Yeah. So the next part is where we're gonna, starting from that solution, we're gonna do an MCMC parameter exploration to get rough error bars and best fits of those. And so the first step, I think, yeah, is there's a part of the notebook where it says instantiate posterior. Should run pretty quickly. And then we're calling the MCMC. So this is the part that will take a little bit of time, where it's actually exploring the parameters around the solution. And so this is, by the way, this is the part that was breaking when I was trying to use the new MC. But now it's fixed the version. We're okay. So it gives us corner plots. Now, a word of warning here. When you're using MCMC, I think both for radial velocities and for orbit fits. These are the spread in the histograms are not your true error bars. These can really underestimate their uncertainty. So for example, if we look at, I made a note of this and I was talking with Jake Singh about this over email, especially for long period planets. These bits can really underestimate the errors so the distributions that come out of the MC are not going to be reliable as error bars. So don't entirely depend on those. For example, the period for the second planet, somewhere in notes. Okay, so the real period of the planet that was in that data set was 1,443 days. It actually got that within, we were 2 days off from the MC in that. But still, it underestimated the errors, right? Because 1 day is plus or minus 1 day. That's our range from the 14% to 84 percentile. But the second planet, the outer planet, gave us an error of only 6 days, but it actually doesn't even encompass the true value.
Oh, yeah.
So for these longer period planets, just watch out for trying to overinterpret these distributions as actual uncertainties. And I didn't even compare the other ones. Those would also probably be similar lessons from those. And we do the nice corner plots like we got for Orbitize.
Is that a well-known problem, which is just some errors?
When I was talking to Jake Singh about this, he seemed to not be surprised that, like, for longer period planets, especially in a multi-planet system where you have strong signals from more than one planet, you just cannot rely so much on the MCMC histograms for those.
We're using this on paper we're about to publish, so thank you.
Okay. And then the last stage, we just make some nice plots, ready to send it to FJ, right?
Yeah, I know.
You have your 2 planets.
I love the plots.
Pretty nice looking.
There's some, so in panel B, the residuals,
Oh yeah.
possibility of a longer period trend there.
That's a great point. So there was, remember we were talking in Ginelli's data set, there's a planet E. So that outer planet, that's a 10 AU semi-major axis, is not going to show up necessarily in the radial velocity. We don't have a huge time baseline, but you'll see a trends.
Yeah.
That probably is.
Yeah, mine is not plotting is the residual. It's not doing fit to that.
It might be, it honestly might be random because every run of the MCMC is going to be a little different.
It's so low that,
So maybe that's not significant. Maybe we're over-interpreting that.
Well, I'm just looking at my eye at the scatter of
It's
the
sort of
light.
looks like it might be.
That was
Yeah,
the
mine's like yours.
I
Yeah.
think it might be.
You can
Did anyone else get a clear downward trends?
Well, you can, you're looking at that. I was looking at those for the
No,
entire.
yeah, no, I
Mine
agree
didn't fit
too,
it,
but
but-
like
You're also.
So I have a special version.
you're right, yeah.
Yeah.
I did notice
It's like
that.
that. Yeah, there could be a far long period.
Yeah, that's,
For me.
Yeah, which those are awesome.
I thought maybe it was a scale thing. It's not even on
We run, no, I
No,
don't
that's gotten
in that case,
Oh, yeah, your
This is
residuals
that's
why there's a
fake
rocker.
data or real data?
Fake data. Okay.
So how come your residuals are not from?
Otherwise, I'd say you should image this.
That's, I don't know.
you should sleep at.
That's a great question.
probably.
Yeah, there's an offset.
Really, I don't have.
I wonder if, honestly, if the version changed since the day ago. I mean, it's possible that they changed something else.
My errors are guilty.
So that is that's all I know about Radville. I'm not, unfortunately, I'm not a radial velocity expert, so I can't give much more insight into that. We didn't.
Unfortunately, you aren't, because I was curious, but we don't have enough time, so never mind.
We have to like pretend that
But who would you suggest talking to? The people that wrote it?
Ben Fulton, he's at IPAC,
Oh, okay.
who is, yeah, I think he moved there
Also Sarah.
not very long ago.
Sarah too?
Yeah,
Sarah
she
Bonds.
also worked on Radville. She's a co-author.
Yeah, they have a very good GitHub page. They actually answer issues.
Yeah, check the page, yeah.
It's the same as Orbitize. They just answer right away.
Well, I mean, related to that, I mean, we're assuming no RV jitter?
Great question. So in this simulation, there was no stellar jitter.
Okay.
And we're actually making, in the next round for the official challenge, there will be jitter.
The challenge as of Sunday? There will be jitter. All right.
Yeah, there will be.
And it's a lot easier.
We made a push for that. We realized it was a little bit too optimistic.
Although I don't think it, for long period planets, my sense is that it's not really gonna amount to that. Still should
I
have.
need to understand jitter for my understanding.
Right.
That should be fun.
Did people get different periods for me? I'm just curious. So,
Oh,
for example,
What was the real
a
ones
little
again?
bit, but
all right. So
yeah.
the real values.
22.
The real value, 4,709 days.
I got
It's a lot shorter.
47.22.
Oh, you're closer.
47.22.
Wow.
Yeah,
So maybe
40 You got 47?
40.
Yeah.
expecting my version is one day older than yours.
No, but I installed mine yesterday. I didn't install.
Yeah.
I didn't install Radville until like yesterday.
I installed.
today.
Well, I did install, to be fair, on the train ride here, which was
So-
Tuesday night.
Yeah.
So
At least 12 hours older than ours then. Yeah.